Good afternoon, good morning, or good evening to everybody, and thank you for joining us for this MOX Colloquia. I'm Alfio Quarteroni, and of course, this is a very sad day for Europe. This is even a more terrible day for Ukraine. And I think that we need to hope and pray that this absurd war will end immediately, right? We are of course very fortunate because we are scientists and we love our work and we have the passion for what we are doing, and we can concentrate on our own research. And today we are even more fortunate because we have the chance to have the opportunity to have an outstanding colleague, Professor Karen Willcox, who accepted our invitation to give a colloquium in our MOX colloquium series. So thank you very much, Karen, for accepting our invitation and for joining us. It's very early for you, and we are all very glad that you are here. And I'll let Paolo, my colleague Paolo Zonino, to introduce you and to chair this session. Thank you very much.
Thank you very much, Alfio. And as you said, it's a really true honor to welcome Professor Karen Willcox to the MOX Colloquia. Let me spend a few words to introduce the scientific achievements of Professor Willcox before we start. So Professor Karen Willcox is director of the Oden Institute of Computational Engineering and Sciences, Associate Vice President for Research, and Professor of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin. Prior to joining the Oden Institute, she served as a professor of aeronautics and astronautics at the MIT, and she was the founding co-director of the MIT Center for Computational Engineering, the associate head of the MIT Department of Aeronautics and Astronautics. Her scientific leadership in computational science and engineering is recognized by various funded projects by the most prestigious US funding agencies, institutions, and high-tech industries. But Professor Willcox is also a leader in education and innovation. For example, she is a recipient of a first in the world Department of Education grant that developed, deployed educational technologies in the community colleges, among other recognitions in these fields. For all these outstanding achievements, she's the fellow of the Society for Industrial and Applied Mathematics, fellow of the American Institute for Aeronautics and Astronautics, and a member of the American Society for Engineering Education. Finally, she was awarded member of the New Zealand Order of Merit. So, Professor Willcox, thank you very much for being with us today. The floor is yours.
Wonderful. Well, thank you very much for the kind introduction, Paolo, and for the welcome, Alfio. I echo Alfio's remarks. This is a very sad day for Europe, but nonetheless, it's great that I can join you virtually. Of course, it's not as good as coming to Milan, but wonderful to join you virtually and share some of our work. So let me go ahead and share my screen. This should all work by now. And I should also say, you know, I know we have some time for discussion at the end, but if you would like to ask questions through the talk, please feel free to do so. And maybe you can raise your hand or use the chat function, and I'll ask Paolo to keep an eye on the chat function there. And Paolo, please feel free to interrupt me if somebody has a question that they want to interject. All right, so let's go ahead and get started. Before I start, I did want to just take a minute to introduce the amazing young people that I work with who have contributed to the work that you're going to see here today. Let me just reclaim what's going on here with my Zoom screen. There we go. So Unit is a postdoc with me here in the Oden Institute. Unit did his PhD with Hans Bungartz at TU Munich. Rudy Kielen is another postdoc here with me at the Oden Institute. Rudy did his PhD with John Dolbo at Duke. Cheng here is a collaborator. We work with Cheng on the rocket combustion examples that you'll see. He's an assistant professor at the University of Kansas. Boris Kramer was a postdoc with me for many years. He's now an assistant professor at UC San Diego. Parisa Kodabakshi is another one of my postdocs here at the Oden Institute. She did a PhD with J.N. Reddy at Texas A&M. Shane is one of my current PhD students here at the Oden Institute. Benjamin was another postdoc with me for many years, now an assistant professor at the Courant Institute. Elizabeth Chan was one of my PhD students. She's now a von Karman instructor at Caltech. And Renee was a master's student with me at MIT, who I could not convince to stay and do a PhD. So Renee's now working for Garmin. So with that, here's the agenda for today. I just want to make just a very few opening remarks about learning from data. And I think I'm talking to like-minded people in this audience, so probably don't need to belabor those points too much. Then talk a little bit about reduced order modeling, why it's important. Again, I expect that the audience is already very familiar with so much of the groundbreaking work in the field having been done in the group there in Milan. And then talk to you a little about our work, the method that we call operator inference, where we're really trying to bring the best of the worlds of model reduction and machine learning together to be able to learn predictive reduced order models. Okay, so let me start off with this slide. So scientific machine learning, this is a term that we hear around these days. And what is scientific machine learning? Really, it's around considering the opportunities and the challenges of machine learning when it comes to complex applications across science, engineering, and medicine. So of course, machine learning is an incredibly hot topic right now. We've seen machine learning have tremendous impacts in many different areas of society. And with that has come a lot of excitement in applying machine learning methods and applying machine learning ways of approaching problems to our challenging problems in science, engineering, and medicine. But of course, our problems in these fields are very different to the problems where machine learning has been so successful. And this notion of scientific machine learning really tries to draw out those differences and really emphasize the point that we can't just take machine learning methods that have been successful elsewhere. We just cannot take them off the shelf and apply them in our complex scientific engineering and medicine problems. The picture here, this is a report that was published early in 2019 by the Department of Energy. I was one of the authors of this report that, again, a few years ago, really thought about what are the basic research needs for scientific machine learning. So again, I think I'm already talking to a community who understands this very well, but just to really quickly emphasize some of the points of what makes our scientific problems so challenging along the bottom of the slide here. Of course, the need to respect physical constraints. And again, if we think about places where machine learning has had so much impact, these are often problems for which there are no models, for which there are no physical constraints. But that's certainly not the case in the problems that we're targeting. So respecting physical constraints, embedding domain knowledge are both absolutely essential. Bringing interpretability to results, let me put on my hat as an aerospace engineer and emphasize that we have incredible computational models and computational algorithms and computing power in the hands of engineers, in the hands of designers. But computers don't design airplanes, people design airplanes, and computers are an invaluable aid to the engineer, to the designer, but that the need for whatever we do with our computational algorithms to be interpretable, to be explainable, to be traceable, to be understandable, and ultimately to interact with a human is absolutely essential. I think more so in engineering, again, maybe than in other applications of machine learning where there may be higher degrees of automation. The fourth one here is a really big one, and it's, I think, a point that many people don't appreciate, which is that we hear this term big data, and yes, we live in the era of big data. And again, speaking as an engineer, our systems have got advanced sensing capabilities. We have more data about our systems, for example, about our aircraft than ever before. But despite having a lot of data, the data are absolutely still very, very sparse. They're very sparse in space. Again, if you want to think about an aircraft, the sensors that are distributed over the aircraft are often spatially sparse. They're also often sparse in time. They're almost always indirect. We can never as an engineer, measure exactly what it is that we're after. We almost always have to take an indirect measurement and then solve an inverse problem to try to get at what's going on. The data are almost always noisy, and again, they're incomplete. And so then sometimes people say, well, it's just a matter of time until we have enough data. So I really believe that in our challenging scientific problems, we will never have enough data. First of all, the data are not free. Putting additional sensors on board an aircraft adds cost, it adds weight, and it adds power requirements. And second of all, getting data is often very intrusive. So again, back to this point about the data being indirect. If I want to characterize the structural health of an aircraft wing, I cannot break open the wing to see what's going on. If I want to understand in a medical setting what's going on with a patient, again, we can't sort of open a person up to see what's going on. And we certainly can't think about the temporal aspects of bringing patients in and subjecting them to tests every minute of every day. Similarly, in our natural environment, we really can't think about sensors covering every part of our ocean. So yes, we live in the era of big data, but our data when it comes to these most challenging problems in science, engineering, and medicine are, and I believe always will be, never enough. And then the last two, of course, is the real sort of kicker for us, which is not only do we not have enough data, our job as decision makers, as engineers, or as supporting medical decisions are to make predictions that go beyond the limited data we have, to make predictions about the future, to make predictions about what a system might do under possible future scenarios. And because those predictions support high consequence decisions where people's lives literally are at stake, we have to understand the uncertainties. We have to quantify the uncertainties and factor that into everything we do. So, of course, this is a very big ask to do all these things, but as Alfio mentioned in his opening remarks, we as researchers love what we do. And I look at this slide and I think, wow, there's so many wonderful problems to work on involving mathematics, computing, and then the domains of engineering, science, and medicine, and advances in these different areas can really make a difference to what computing can do for us across society. So as I was talking through all those challenges, you probably have an undercurrent of a theme, which is data and black box machine learning is never going to be enough. And that we absolutely have to be thinking about bringing our physics-based models into all of this as we think about scientific machine learning, as we think about learning from data for complex scientific systems. So, of course, this is now an idea that's, I think, pretty widespread in the community, that there's a lot of appreciation for having to bring in physics-based models. I want to make one point that goes beyond that, which it's not just about the physics-based models itself, but it's also about bringing in all the existing theory, formulations, and methods of the field of computational science. For example, the long history of inverse problems that stretch back decades, the theory that we have when it comes to solving inverse problems in the context of systems governed by partial differential equations. Again, I feel that often there are aspects of things that have been done in computational science for many decades that are not known or that are ignored in our community's excitement to reach for machine learning. So the picture that you see here, this is a very brief comment piece. It's 2.5 pages that I co-authored together with my colleagues Omar Gattas and Patrick Heimbach, where we really tried to make this point of the essential nature of bringing not just the physics-based models, but also things like inverse theory. All right, so that's all wonderful. Physics-based models are powerful. They bring predictive capabilities to us. But of course, one of the challenges that we have to grapple with is that these models can be very computationally expensive. And as we think about applications where we have data, where we want to learn from data and deploy predictive models, it's often the case that the predictive physics-based models that we have are too computationally expensive. They're just intractable. The nice pictures that you see here, this is some of the work that we do on an Air Force project that's looking at rocket engine combustion. And just to sort of put a sense of what it means to be computationally expensive, despite the incredible advances in the algorithms and in computing power that have now given us very powerful simulation tools to simulate the complex reacting flow inside a rocket engine, a single simulation, the estimate for a single simulation using supercomputing power, sort of using our very best, for a full engine is on the order of about 3 months. So 3 months for a single simulation. And now you put yourselves in the shoes of the designers who don't want to do just one simulation, but who want to do many, many thousands of simulations, varying different geometry parameters, varying different operating conditions, exploring the design space, and supporting the decisions of the design decisions that will design the next generation of rockets that I hope will be taking humans back to the moon and beyond. Clearly, at 3 months per simulation, that's not going to get you very far. So this is where reduced order modeling comes to play. And again, I know I think folks on the seminar are very familiar with reduced order modeling, but let me say nonetheless that again, as the community gets so excited about machine learning and in its role in coming up with surrogate models of sort of fast models, to recognize that the computational science community has actually been doing this for many decades, and the field of reduced order modeling is very much at the heart of this. So reduced order modeling is going to be a critical enabler in this idea of learning predictive models. And again, the history of reduced order modeling, I think, has a lot to teach us about how we might approach learning from data for these challenging problems. So what is reduced order modeling? Again, probably a familiar concept, but we have here on the left some kind of high fidelity physics-based simulation. Maybe it's that very expensive rocket engine simulation that I was showing on the previous slide. The dimension of this problem is very large, millions, even billions of degrees of freedom, often because this model is a discretization of partial differential equations that encode the governing laws of nature. And solution time, minutes, hours, days, maybe in these extreme cases, even weeks or months. So the idea is to come up with a reduced order model. And the way that we will derive that reduced model is through the mathematical framework of projection, which I'll touch on in just a second. But the idea being the reduced order model is of much lower dimension and can be solved much, much faster. 3 main steps in reduced order modeling: a training step where we're going to query or solve this high fidelity system in some way to generate training data. In the reduced order modeling world, the training data are usually called snapshots. So these will be representative high dimensional solutions of the system that we're trying to approximate. A second step where we identify structure. And there are a variety of ways we can think about identifying structure, but in many cases, what we're looking for is dimensionality reduction. We're looking for some kind of low complexity or low dimensional structure within the high dimensional space that's defined by our training data. And many, not all, but many methods use a linear subspace, use a low dimensional basis to identify that structure. And in what I show you today, we're going to be simply working with the proper orthogonal decomposition, the POD, which again is just a linear basis that defines a low dimensional subspace in the large state space defined by my original high dimensional snapshots. So if I were to stop here, we could be talking about a machine learning method, a training step where there's data and then some kind of identification of structure using your favorite machine learning method, whether it's based on deep learning and neural networks or based on something else. But with reduced order modeling, there's a third step, and that third step is the projection step. And this third step is really critical because when we now go back to the governing equations, back to the partial differential equations, and mathematically project those equations onto the low dimensional subspace that we identified in step 2, it's this third step that injects the physics back into the reduced model. Yes, the reduced model is a mathematical approximation. It's operating in a mathematical coordinate space, but the projection brings the physics back into the reduced order model. And not only that, by doing the projection in an appropriate way, there are large classes of problems for which rigorous error estimators, sometimes even error bounds, can be derived so that we can then use the reduced model to issue predictions for conditions outside of training and do so with quantified confidence. So again, just to emphasize, this is really where I see reduced order modeling and machine learning as actual intellectual neighbors in many ways. But this third step, the reduction via projection, is where reduced order modeling brings back the physics into the approximation. Okay, so that's all well and good. So, you know, what is a physics-based model? I think this is something that is very familiar to everybody on the call. The physics-based model is what encodes the governing laws. It encodes the domain knowledge. It embeds the concepts of time, space, and causality. I often read papers where people are discovering physics or learning physics, discovering hidden physics. There are absolutely a large class of problems for which we do not have good models, particularly in the biological sciences. And so that is a very important line of work. Today, I'm really going to be focusing on the perhaps larger class of problems for which we do have good models. And this is particularly true in engineering. We don't need to learn or discover the physics because imperfect as they may be, we actually have pretty good models often to describe our systems. The issue is, of course, that solving these models can be difficult and very, very expensive. So a physics-based model maybe often comes to us in the form of partial differential equations. When we discretize using our favorite method, we might get a system that looks something like the system shown down here. And for the rest of the talk, I'm going to work with the semi-discrete form just because it's just much easier at the presentation level. So this semi-discrete form here, where X now is my discretized state, containing whatever the physical states are at my spatial grid points. And so X is going to be a very high dimension, think millions or even billions of degrees of freedom. I've written this as a dynamical system. So here the time derivative of X. I've separated out a linear term here, AX, where A is now the discretized linear operators, an input U that will come through some kind of forcing or boundary condition with the operator B that maps the input to the evolution of the state, and then everything else, all the nonlinear terms sitting here in F of X and U. So again, that's our high dimensional model. To come back to this notion of a projection-based reduced model, again, this should be familiar. Let's start with a linear system. What are we doing? We're looking for low dimensional structure here defined via a linear basis that I'm denoting V. So V is the basis matrix that has as columns in my case, POD basis vectors. I'm approximating my high dimensional state X in that low dimensional basis V, and I'm going to use X reduced here to denote those modal coordinates, the reduced state. And I can substitute this approximation into my system. That's going to give me a residual. I can then enforce this orthogonality condition. And what I'm going to show you today, we're going to be using a Galerkin projection, meaning that this basis matrix W is chosen to be V. And that's what gives us the reduced order model. And again, this is sort of reduced order modeling 101 that I expect everybody knows. But just to reinforce, the magic of projection is that the reduced order model here preserves the structure of the system that I started with. It has the same here linear form, and these operators, this A reduced and this B reduced here, are nothing but the projections of the original A and B onto the subspace defined by the matrix V. And of course, everything is beautiful in the linear case, but we could also recognize that if we had a quadratic model as the starting point, so now let's introduce this quadratic term where H now here is a tensor, and this Kronecker notation, this X cross X term here just represents all the different quadratic products of the state X. And if we were to go through the same thought exercise, which is approximate X in the low dimensional basis V, use the projection, here's the form of the reduced model. And again, we see the magic of this projection framework where the reduced model again has the same structure as the full order model. And this reduced order tensor here, this H reduced, yes, it's a little bit more complicated, but again, it's nothing but the projection of the large H onto this reduced subspace defined by the basis matrix V. And you could imagine that if I continued adding cubic and quartic terms, that that I would see a similar effect taking place, that projection preserves structure. So a projection-based reduced model is really a very special kind of approximation. And why is preserving structure so important? Because the structure is what embeds the physical constraints. Again, I'm writing this kind of in a very generic way as a semi-discrete system, but let's not forget that these operators, these A, this H, these B's, are really representing the governing equations. So depending on the governing equations we started with, our full order model is going to have different structure, different linear or quadratic and also nonlinear structure that is reflecting the physical constraints. Okay, so again, at this point, I've told you nothing new. This is kind of reduced order modeling 101. But what we're going to take from this is that a projection-based reduced model, again, is a very powerful way of thinking about embedding the physics into our approximations. Now, reduced order modeling has seen a tremendous amount of development and success in academia over the last 2 to 3 decades. But other than there's a few notable exceptions, but otherwise, reduced order models really have had limited impact in the I want to say the real world. And particularly as I look, for example, across the aerospace industry, there's been relatively little uptake of reduced order modeling methods. Why is that? It's because these methods are very intrusive. In order to compute a reduced model, I have to go into the complex code. I have to be able to get a hold of these operators, these A's, these H's, the nonlinear term in some way, and I have to be able to compute the reduced order model by doing these projections. And while that may be fine in your university lab, where it's a code that you've written yourself or a code that's maintained by your group, if you're Boeing or Lockheed or NASA, what you have are giant codes, often written in Fortran, that are just sort of have evolved over many decades, let's say. And it's really not practical to think about going into the code, accessing what you need, and developing the reduced order models in this way. And this is what machine learning has taught us. To go back to my opening remarks, there is so much excitement about bringing machine learning into our modeling of scientific and engineering systems. One of the reasons I think there's so much excitement is because it's easy, it's accessible, it's non-intrusive. You don't have to spend years going through somebody's Fortran code to try to apply machine learning. Machine learning operates in a sort of a black box, non-intrusive way on the data. So it's this observation that inspired us to develop the method that we call operator inference, which is to say, can we use that mantra from machine learning, which is to say, let's be non-intrusive, let's make it easy and accessible for people to apply the method, but let's not throw away everything that we know from model reduction about, I would call them responsible ways to inject physics and to approximate systems governed by partial differential equations. So let me give you the kind of the summary up front. We already have many of the ingredients, and now actually putting them together is going to be relatively straightforward. The operator inference problem, again, is given a physical or natural system with known governing equations. And again, I want to emphasize there are certainly a large class of problems for which we don't have good models, and I am not addressing those problems. We're thinking about the situation in, for example, in my aerospace engineering problems, where we have known governing equations, and we're trying to come up with an approximation with a reduced order model that's faster to solve. And we're also given a set of data. And then what I show you today, the data is going to be simulation data. So the data will be coming to us in the form of state snapshots. But the data, and I think you'll see it as we go through the formulation, could also be experimental, or it could be a combination of the two. And in fact, we have ongoing work in our Air Force Center of Excellence, where we're really looking at how one takes both experimental and simulation data for a combustion problem and combines them in the operator inference framework. So given these two things, our goal is now to infer a reduced model. So we're not going to derive a reduced model via projection, but rather we're going to learn it from the data. But we're not going to learn it from the data in a black box machine learning style approach. Instead, we're going to use the physics to define the structured form of the reduced model we seek. We're going to use what we know from projection-based model reduction to cast this inference problem in a reduced coordinate space, and also to give us a window into some of the theory that comes along with projection-based model reduction methods. We're going to recognize that this is an inverse problem. And again, to go back to my earlier remarks, there are decades of work in inverse theory that will guide us into understanding the ill-posedness of the problem, the need for regularization, and how to solve this inverse problem in a numerically responsible way. And at the end of the day, all of the operator inference, all of the steps of operator inference amount to numerical linear algebra, which means that we can use off-the-shelf packages and also do things very efficiently and at very large scale. And again, to sort of give you the final result right up front, the final result is going to be that we solve a linear least squares problem to infer some operators that define a reduced model. And I'm going to show you now how that comes together. Okay, so again, starting point, a physics-based model, again, typically described by PDEs or ODEs, and this lens of projection. There's a second step that you see in here that I don't have time to talk about today, but it's a very important step, and I think actually sort of one of the fun parts of the method, which is to go back to the earlier slides where I showed the linear model and the quadratic model, and I showed that, I reminded you that projection preserves structure for systems that have this polynomial structure. And I can imagine many of you were sitting there thinking, okay, but what about if you have a nonlinear system that doesn't have this polynomial structure? Well, one of the ingredients that we've been using is the notion of variable transformations in terms of just changing the variables, and also the notion of lifting, which is the idea of bringing in extra variables that you don't need from a sort of PDE modeling standpoint, but in doing so, you expose this polynomial structure in the system. And again, I won't have time to talk about it, but let me just give you a one to think about, which is probably everybody's familiar with the Euler equations that describe the inviscid compressible flow. And naturally, we would typically work in the conservative variables, density, momentum, and energy. Perhaps we would work in the primitive variables, density, velocity, and pressure. And of course, the Euler equations are a nonlinear set of equations. Well, it turns out, and this is well known in fluid dynamics, if you work in the specific volume variables, 1 over density, the specific volume, the velocity, and the pressure, then the Euler equations become quadratic. And so there's an example where choosing to work with 1 over density instead of density exposes this quadratic structure in the governing equations. And again, to emphasize the real power of machine learning, of a machine learning view of the world, of course, I cannot show up on Boeing's doorstep and tell them, I need you to rewrite your codes using 1 over density instead of density. It's just completely intractable, not to mention the fact that it's probably not even going to be a sensible mathematical way to discretize the equations. But because we're taking this view of inferring the reduced models, learning the models from data, we can very easily play these games with the variable transformations on the snapshots. So these variable transformations will be applied to the snapshots, and we will get the variables that we want to work in. The code will output density, and we'll take 1 over density and feed that into our reduced modeling. But again, these 3 ingredients, looking at the PDEs, thinking about the variables I should be working in, and then knowing that I'm looking for a projection-based reduced model, that defines the structure of the reduced model that I'm looking for. I'm going to have linear terms, I may have quadratic terms, I may have forcing terms. And so now I can find this reduced model by learning it from data and do it in a non-intrusive way. But I won't be just learning a black box generic representation. I will be learning a structured reduced model that has the form that's given to me by the governing equations. How now do I actually infer these reduced operators? So we're looking for A hat, B hat, and H hat. We're going to do it by solving this optimization problem. What you can see is that this optimization problem is a minimum residual statement. We're looking for the reduced order operators, the low dimensional operators, the A hat, the B hat, and the H hat that define the reduced model. And we're feeding in data. The data here are snapshots. This is the snapshot data, which might come from simulation or experiment or a combination of both. And the hats on the snapshots here indicate that they are snapshots in a reduced order coordinate space. So I'm going to need to take my high dimensional snapshots, compute that low dimensional basis, and then project the snapshots onto the low dimensional basis to get the modal coordinates. And of course, all of that can be done non-intrusively. And then what you see is that this is a minimum residual statement. We're taking the snapshots, their time derivatives, and any forcing that was used to create them, substituting that into the postulated form of the reduced model, and then minimizing the residual. And using this minimum residual formulation, what you notice is that the things we're solving for, the operator, the coefficients of the operators A hat, H hat, and B hat, this is now nothing but a linear least squares problem, which of course is going to be easy to solve even at large scale. Okay, so this is kind of the PowerPoint simplified view of the formulation to just to keep it simple and help convey the ideas. Of course, there are many details here that are important. One is regularization is key, is absolutely key. And in fact, for everything other than the simplest problems, this must be regularized in order for the operator inference problem to work. And of course, you can regularize in such a way that you maintain it as a linear least squares problem. Benjamin Perstoffer has some very nice work where he shows that if you generate the data in a particular way, there's X hat here, the X hat dot that's feeding in, you actually can provably recover the intrusive POD reduced model. In other words, the A hat that you learn here, you can provably recover, you can show that you recover the V transpose AV that you would have gotten if you did the intrusive projections. And why is that important? That's important because that now starts to connect this non-intrusive learning of a reduced model with the tremendous body of theory that exists for intrusive reduced order modeling methods. Okay. All right, so let me just show you quickly one example of a large scale problem that we've done, and then I want to go on to show you some of the newer work that we're doing to make this approach more powerful for another class of problems. But let me just show you so this again back to the problem of modeling a rocket engine, and we're going to be modeling just a single injector within a rocket engine combustor, so it's a tiny piece of the engine. The governing equations here are the Navier-Stokes equations for the flow, and then we've got reactions. So then there's also the equations that govern the conservation of chemical species. And again, the starting point is to sit down and look at these equations and look at the terms that show up, to think about the variables we want to work with. And again, we use this trick of working with the specific volume, of working with 1 over density, and recognizing that when you work with 1 over density, velocity, pressure and then the chemical concentrations that many, not all, but many of the terms in the PDEs have a linear or a quadratic form. Let's see. So the code that generates the high fidelity data is called GEMS. This is a code that was developed by Purdue University and that the Air Force use. Again, this is a giant Fortran code that we don't have in my group. We don't want to touch the insides of that code. And in fact, we don't even have it. Our collaborators generate the training data for us. The training data, again, are these full state solutions. 2.6 million degrees of freedom in the spatial grid. I should say that I don't think the spatial grid is as finely resolved as it should be, but you get a sense of just how expensive these models are, because even running with this spatial degrees of freedom and getting snapshots over 3 milliseconds is an enormous amount of CPU time. I mentioned the transformations that we use for learning the reduced order models. And so at the end of it, what do we have? We have a snapshot matrix with 21 million degrees of freedom and 3,000 snapshots over 3 milliseconds. We also have an additional 2 milliseconds of snapshot data. That's another 2,000 snapshots that we're going to use for testing the performance of the reduced model. Here are just a few plots to give you a sense of how well we can do. What we're looking at here are two different probes in the injector, one up here and number 2 down here. In the black, you're seeing the CFD. In the orange, you're seeing our operator inference reduced models of dimension 80, 100, and 150. The line here at t equal 18 milliseconds denotes the end of the training period. So up until this point, the reduced model's issuing predictions, but it's doing so for conditions that it saw during training. And then beyond this, we're now predicting out into the future. So you can see that in pressure, we're actually able to do pretty well and get reduced order models that are predicting what's going on in the pressure quite well. Temperature is much harder to get because the temperature is a transport dominated quantity. And you can see here again the CFD. This is the 20 million degree of freedom CFD calculations with the reduced models. And certainly you can see as we start to go out into the prediction horizon, we're capturing some of the large scale structures, but again, temperature much harder to get right than pressure. We've also done some back-to-back comparisons with POD DIME, which you might say is one of the state-of-the-art intrusive reduced order modeling methods. Our collaborator, so Cheng, has spent the best part of several years implementing POD DIME into the GEMS code. And again, to emphasize this barrier of entry of reduced models because of their intrusive nature is huge. The takeaway from this slide is that we, with operator inference, we again, send us a bunch of data, tell us what governing equations you're solving, and we can learn reduced models. And operator inference, we're able to do just as well, if not sometimes better than the intrusive POD DIME reduced order model. So we've been deploying the operator inference methodology in a variety of problems. We're working with the Air Force right now on a rotating detonation rocket engine. And this is very, very challenging physics. And again, complex codes where we're able to learn reduced models from data. We're working with Lockheed on fluid structure interaction for a wing. Here we're working with NASA's Fun3D code. And again, able to successfully get reduced order models learned from data. We also have a variety of work in material and manufacturing applications through a Department of Energy center. We've been looking at additive manufacturing with Oak Ridge National Labs and with some phase field models. So let me see how we're doing. We're at 8:45. So in the sort of maybe remaining 5 to 10 minutes, I wanted to tell you sort of add a little bit onto this, which is to say, okay, we've got the baseline idea, the structure of the model, and the predictive power that the physics bring us. But we've set everything up in such a way that we can do it non-intrusively, inspired by the success of machine learning. But we can ask the question, what more can machine learning concepts bring to model reduction? And I want to touch on a question that again may be on some people's minds, which is everything that I've told you today is sort of hinging on this beautiful power of projection onto a linear subspace of a model that has polynomial structure. So the polynomial structure maybe seems like one blocking point, but we've talked about how variable transformations can address that. Another blocking point is a linear subspace rich enough? And of course, we know that there are many problems, and this Cahn-Hilliard phase field model problem that I'm showing here is a great example of one. There are many problems where a linear subspace is just not rich enough to be able to give us a good predictive reduced model. And how do we see that? We'll see that when we take our snapshots, if we compute the singular values, we see that the singular values decay slowly, and our low dimensional model, our low dimensional subspace would need to have many, many hundreds of degrees of freedom in order to explain enough of our snapshot data. So what can we do for problems like this? Again, to talk about the history, there's been many efforts, many successful efforts to address this challenge throughout the model reduction community over the years. So there are adaptive model reduction methods, there are interpolation methods, there are methods that employ nonlinear manifolds, dictionaries of reduced order models, problem-specific registration, domain decomposition. There are many, many approaches that have been developed. But again, these approaches have all been intrusive. And so now the question is, can we think about some of these approaches and maybe bring one of them together with the operator inference non-intrusive way of approaching the problem to come up with a formulation. So let me show you what we do in a method that brings localization to operator inference. So again, here's the Cahn-Hilliard phase field model that we're going to work with. And again, I want to emphasize, we sit down and we look at the PDEs and we say, okay, for this particular model, here's a cubic term, here's a linear term, and here's another linear term. So the form of the model I'm going to be looking for, the form of the reduced model will have a linear and a cubic term inspired by the partial differential equations. What I'm going to do now is just what I did before. I'm going to have data generated by my high fidelity code, but now rather than computing a global POD basis to try to explain that data, I'm going to use a clustering method where I say, can I now, instead of learning one linear POD basis, let me first cluster these snapshots and learn multiple local POD bases. And again, you see the steps here. This is nothing but linear algebra. This can all be done operating on the data set that I have. Now that I have the clusters, you can see where we're going with this. We're going to learn now multiple operator inference reduced models. Again, here's that linear cubic form of the reduced model that we're learning. And now the reduced operators, the A hat and the G hat that I'm learning here, have got a P index where P is going to denote the cluster that I'm in. There's a second step that I need to do here, which is I need to train a classifier, because once I have all these localized reduced models, I'm going to need to know which one to choose at a given point, and I'm also going to need a way to go between them. So again, we'll train a classifier. The classifier is going to map from the low dimensional state into a cluster index, and that needs to be also trained at this offline stage. But again, to emphasize, here's the operator inference problem that looks for those reduced models. I've written it out here for the linear cubic form. Here are the regularization terms that we need to introduce. And again, this is nothing but a linear least squares problem to infer those localized operators. Now we have learned multiple operator inference models. We can now think about how you would solve this reduced model. So now we're in the online phase. So the first step is we're going to have to compute this indicator. Again, this indicator is just a representation of the low dimensional state in a common basis. Evaluate the classifier. The classifier says to me, use model number 5 or use model number 8, depending on where I am in state space. Once I've picked out that model, the piece reduced model, I just now solve it, and then continue repeating. And of course, you have to be careful as you jump from model to model to ensure a mapping from one state to another. And again, this can be done pretty simply with projections. So all of this is inspired by the localized reduced modeling methods that exist in the literature, that have been in the literature for decades, but we're now doing all of it in such a way that it's non-intrusive. It's done entirely from data. And just to give you a sense of how well does this work, I love the plots of the singular values because I think they tell so much of the story. Again, for this Cahn-Hilliard problem where we have snapshots seeded with different initial conditions, here's the global basis, the slow decay. And again, in order to capture enough energy in this basis, we would need hundreds of modes in the reduced model. If we're willing to construct 8 localized models, that's the blue bands here, you can see how much faster the singular values are going to decay. And there's variability here because of the different, sort of the randomness introduced by how we might cluster and compute the basis. And if we wanted to go to having 32 local models, then we get to the red one that you see here. And now we're looking at singular value decay at the sort of more comfortable level where we can now get reduced order models with very low dimension, again, with the localization. And just again, visually, here's an example of a reduced model with 32 localized clusters and a dimension of 15. And here's just one sort of evolution of a full model. And even this very challenging problem with these moving interfaces, the reduced model is able to do remarkably well. If you look very closely, you'll see some differences in the solutions, but it's really pretty remarkable just how accurate the reduced models can be with this localization. Okay, so let me just close with a few closing thoughts. One of the very exciting areas and one of the current focuses in my research group, and I know this is also of interest to many people on the call, is the idea of digital twins. I'm excited by digital twins because of the potential they have to really revolutionize the way we use computing across so many different applications in science, technology, and society. And what's also exciting is the way the idea of a digital twin goes beyond just engineering. And in my group, we've been working on self-aware aerospace vehicles, and we've just started a new project on digital twins for space infrastructure, but also thinking about how digital twins can play a role in medicine and in understanding our natural environment. A really, really exciting time. So of course, lots of progress, but many challenges. And it's wonderful that there are many challenges that remain for us as researchers. We still have a long way to go to really have predictive modeling for complex systems at scale. Despite what you read sometimes in the newspapers, we still are a long way away from being able to simulate something like a rocket engine at the scale that is truly needed. And of course, computing power will get us some of the way, but the mathematics and the algorithms has to play a huge role in moving us forward. Validation, verification, uncertainty quantification, so essential, especially as computing starts to inform more and more critical decisions. Again, we need to think about how we integrate data, models, and ultimately decisions across multiple scales. I think there are a lot of very interesting and open questions around optimal sensing strategies, especially as we start to think about digital twins and what that means for integrating our sensor design and the way we collect data for our systems. And then finally, this legacy codes and processes, this should not be underestimated as a huge barrier. And again, I want to say something that I've said a couple times, but I think it's important. Computational science has revolutionized the world in so many ways, but in many places, the state-of-the-art computational science has not been adopted because it has not played well with the legacy codes and the legacy processes that are very much embedded in many, especially in many engineering companies. And again, I think we as computational scientists have something to learn here from the computer scientists and the non-intrusive ways in which they craft their approaches. So with that, let me stop. If you want to grab any of the papers that touch on the work I've mentioned, you can do so from my website. But Paulo, back over to you, and I guess we can take some questions.
Thank you. Thank you very much, Karen, really for the impressively clear and inspiring talk. So the floor is open for questions. Alfio, if you want to start, otherwise I have one.
Please go ahead.
Okay, just to break the ice. So I was really impressed by the application of operator inference to this very complex reacting flow problem. And of course, this can be defined as a multi-physics problem. So my question is about the training in the case of multiple physics. How do you do it? You do it in a monolithic way. So you try to infer the operators for all the physics together, or you can envision also to apply some splitting techniques that break down the operator into blocks, into smaller pieces.
Yeah, that's a great question, Paulo. And in fact, the project with Lockheed where I mentioned the aeroelastic for that VAT wing, that aircraft, this is one of the questions we hope to tackle, because there we have the CFD for the fluid, for the aerodynamics, and then the structures. And your question is exactly the question. How do you do it? Do you try to couple at the high fidelity level and monolithically learn a coupled operator? Or do you try to learn the operators and some kind of operator splitting? And, I think the answer is it's going to be both, depending on the situation. And then again, of course, we're not starting from scratch, because reduced order modeling has tackled these multi-physics coupled problems from an intrusive standpoint. And so thinking about, what we've learned from the intrusive world and how we bring that, but just ensuring that whatever, I know I've said it too many times, but ensuring that whatever we do can be implemented by the Lockheed engineer who does not have the capability to go in and modify the codes. And then that's the starting point. And then say, and now how do we bring as much math and as much theory as we possibly can if we're going to be non-intrusive? So I don't have the answer to your question, but your question is exactly the right one.
Thank you very much. Well, so I will maybe give some thoughts to that. Thank you. Any other questions from the audience? In case, just unmute yourself and ask the question.
So maybe I have one question, Paolo.
Sure.
So Karen, thank you very much. I mean, this was very beautiful and visionary, I would say, also talk. I have a question which is more of more a curiosity than a real technical question. You started saying that in many problems of real interest, many problems of real interest are characterized by the scarcity of data, indeed. And of course, you addressed very tough problems. And for instance, if you consider the injector reacting flow model that you have been presenting to us, I would guess that this is one of those examples where it might be I'm just speculating, very difficult to obtain experimental data, right? So, and in the procedure that you have been presenting in this non-intrusive, way of generating reduced order models, if I'm not wrong, but I may be wrong, the data that you're actually using are the solution provided by the full order model, right? So somehow you are not using data, real data, as for instance, our colleagues from the computer science department at Politecnico will use. They conceive machine learning algorithms based on real data. So they don't see any physical model behind, right? So with this approach, you are really embedded into the physical problem, right? And you extract the reduced order model from the physical problem. So one obvious criticism that our colleagues from, say, the computer science department may have is that if you cannot fully trust the physical model. There is no way in your approach to try to get a little help from real data, which will express the real physics. Is it a silly argument, or is there something correct?
No, absolutely. This is an absolutely great point, Alfio. And so let me answer in a few different ways. Of course, every setting is different. Sometimes you have a model that you do trust, and the goal is to come up with a much faster model. And so that's one setting, and that probably fits very naturally into what I've talked about today. Sometimes you have a model that you don't trust or that you know is wrong. And I know I'm being recorded, but I've said this so many times. I don't trust, and I don't think anyone truly believes that the CFD code that we're working with for the rocket engine, it's not giving the right answers. I mentioned that the spatial grid is under-resolved. So much is under-resolved. There are approximations introduced to model the chemistry. And I sometimes say our job is to get the same wrong answer, but to get it faster. So that is sometimes a setting. And then, how do we move beyond that? So experimental data. And so if we talk about this rocket combustor example, you're absolutely right. First of all, it's very hard to get simulation data because it's so expensive. But again, this is where I feel things like decomposition strategies, your work in domain decomposition, the scribe type approach from Tony Patera and from Axelos, these ways of breaking up, even what Paolo mentioned with the multi-physics, of collecting data from smaller pieces of the problem and putting it together has something to play there. So it's hard to get simulation data. It's even harder to get experimental data, as you can imagine, in these very hot, fast moving flows. But this is one of the things we're looking at, which is, and by the way, the experimental data does not come to you in the form of densities and velocities and pressures. It comes to you in all kinds of other strange quantities that I had never even heard of. But we're thinking about, how does one take the wrong imperfect model and the wrong imperfect experimental data in different quantities and maybe put them together, and within the framing of our operator inference formulation, we can add experimental data into that objective function, right? We can ask, find me the reduced model that explains the simulation data and also explains or recovers the experimental data. It's not easy, but that's something we're definitely thinking about. So yes, I think it's absolutely a fair criticism, and but I think there's some hope that we can move beyond that. And I actually think that if we move away from our more rigid, intrusive methods, it actually opens new possibilities to address this by combining the best of both worlds, combining what experiments can predict well and what models can predict well, and maybe in some doing better overall. Yeah.
Clear.
Any other questions or comments? No, I don't see anything in the chat. Or, well, maybe it's time to thank once more Professor Willcox for the really very inspiring and very clear seminar on reduced-order models, and in particular operator inference. Anyway, let's say for further interactions and for the, let's say, interested people, we may have still some time to discuss. So maybe it's time to close this, let's say, official session of the MOX Colloquium, thanking Professor Willcox and thanking all the audience again. Alfio, if you want to say something, please.
Thank you very much. This has been a great, really great talk, and it's a very hot topic. It's something that you cannot escape from. Fortunately, I would say, because it's so many opportunities that stem from the combination of the two words. And you have been showing how you can really embed into our classical world of physics-driven model new approaches coming from machine learning, so borrowing the strategies from machine learning without using the, I would say, the raw method of machine learning, which is data. So this opened the space to even more fundamental progress when we really be able to combine, as you said at the very end of your comment, to really combine with full power the two worlds. And I'm sure that we are going to experience very substantial progresses also for very hard problems like those that you have been addressing today in the near future. So thank you very much.
Wonderful. Thank you. Thank you, Alfio, and thank you, Paolo.
Thank you.